Hello everyone, this is Michal from Airhead and welcome to today's quick session where we will go through the latest questions from subject of meteorology, and all of the questions that you'll see now have been seen in the actual EASA exams in all of the authorities in the past 2 months, and we'll go through 7 questions that I think are quite interesting, and I'll try to give you some extra tips as we go through the explanations and possible answers. So jumping into question number 1, the orographic thunderstorm may occur. And now this is a very interesting question because it unpacks what the thunderstorms actually are. And of course, the thunderstorms are nothing else but highly built cumulonimbus clouds producing very big amounts of precipitation as well as the lightnings. And they generally always pose great risks for aviation. And by law, we are required to overfly them by at least 5,000 feet vertically and at least 20 nautical miles distance horizontally. However, thunderstorms need specific conditions to exist in order for them to form, and there are 3 requirements that you should and need to remember for your exams. These are: you need at least 10,000 feet of unstable air above the freezing level, you need adequate moisture, so for example, there is a moisture front coming from the area of sea, or it has been raining somewhere else and the air has been advected. And lastly, you need a trigger for the uplift, and this is the important one, as the trigger for the uplift will decide the type of the thunderstorm. So if the uplift is orographic because of the mountain, then of course we're talking about an orographic thunderstorm. If the uplift is because of the front movements, then we are talking about the frontal thunderstorm, and so on and so on. So in this case, if all the other conditions are met, the last trigger will decide when the thunderstorm can occur. And in case of an orographic thunderstorm, this one can occur anytime because the mountain doesn't really care if it's day, night, cold, warm. If there is enough of unstable, moist air going and it's being pushed up the mountain and it's condensating, then the thunderstorm can form pretty much at any time, either during day or during night. And now for question number 2. What level of potential ice exertion can be expected when descending through an active CB at flight level 150 when the outside air temperature is plus 3 degrees? So generally remember that if the temperature is below 10 degrees Celsius and the visible moisture is somewhere around us, visible moisture being a cloud, rain, drizzle, fog, etc., then there is a risk of icing. When you'll be flying commercially, you'll see that below 10 degrees Celsius TAT, you will turn on your engine anti-icing in order to avoid possible icing conditions. And secondly, whenever you fly in cumulonimbus clouds, you always expect icing, and CBs are prone to severe icing. And this should always be a red light in your head. When you see a CB, essentially at any level, it's a good indication of severe icing conditions that are possible, and it's also a very good idea in such cases to turn on the anti-icing. And here I just wanted to say that this is mainly because of the supercooled water droplets, which in CBs they are going up and down because the convective air is going very violently in circles inside of these clouds, and these supercooled water droplets will exist anywhere from 0 to minus 40 degrees, and the moment they touch the surface of your aircraft, they will create clear ice and they will degrade the lift potential of the wings and increase your weight dramatically. Here also remember that in questions asking for carburetor icing, these temperatures will be much higher, as the carb icing has to do with the Venturi effect, which drastically lowers the temperature in the inlet in the butterfly valve. And here these carb icing can occur anywhere from 20 to 30 degrees Celsius up to around minus 10 degrees. This is where the carb icing risks exist. And for question number 3, a crew is operating over the plains of Tanzania, Africa at low levels in April. The intertropical convergence zone usually passes through the operating region. Which of the following might be a particular hazard due to the intertropical convergence zone? Intertropical convergence zone is nothing else but a place that has the highest isolation, meaning the sun is hitting it from 90 degrees. And of course it shifts when we have summer in the northern hemisphere, then the air tilt makes it that the the ITCZ moves higher, and then winter is vice versa. The ITCZ moves lower. And of course, because of these very strong rays and a very strong solar energy that is hitting the Earth at the highest angular deflection, 90 degrees, we have the strongest convective movements, thermal movements of air, and they in certain conditions can create very violent thunderstorms and also squall lines, which are associated with ITCZ. And these are main threats when flying through the intertropical convergence zone. And of course, because we are talking about the sun and the energy, midday is when the sun is directly above us, meaning this is when these convections, thermal airs will be strongest, and there is the highest possibility, if adequate conditions are met, for heavy rain showers and even violent thunderstorms. And now question number 4. A strong inversion in the middle troposphere will the vertical development of a CB cloud. Of course, if you have studied meteorology, this question will be extremely simple, and the answer here is stop. So the strong inversion will act exactly the same as a tropopause, meaning it will pose a barrier of very stable air, and this inhibits the development of any convective clouds, and so also the thunderstorms. And CBs being convective clouds, they need unstable air in order to be pushed up. The moment the lapse rates are equalizing, this is the moment when the CBs stop forming, because they can no longer condense and go higher, meaning that if there is an inversion, the CBs and thunderstorms will stop developing, just as if we were talking about the tropopause, where all weather essentially stops. For question number 5, which cloud type may indicate the presence of severe turbulence? And this is another example of a question that, if you know the main principle for the exams, you'll be able to answer all of them. And in 99.9% of the questions, the right answer will be the CB, or any type of a cumulus cloud. In this case, this is altocumulus lenticularis. And remember for your flying and the exams that altocumulus lenticularis and any lenticularis type clouds are the most dangerous ones in aviation, next to Cumulonimbus. Lenticularis clouds indicate the presence of mountain waves, which are forming when the wind is blowing at 90 degrees to a mountain range, creating very violent movements vertically of air all the way up to the tropopause. These mountain waves will go for 3,000 to 4,000 feet per minute up and down, meaning they will cause massive turbulence and also increase the load factor, flying extremely dangerous. So altocumulus lenticularis, these indicate mountain waves, extreme turbulences. Never fly into them. If you see them in an exam in a question like this, always click lenticularis. If not, the cumulus will always be the right answer, as these are convective clouds, so they need very strong uplift and the air moving upwards, which for passengers will cause a turbulence, and for yourself as a pilot. And for question number 6, the diameter of drizzle droplets is less than. So this is one of the infamous questions that everyone talks about once you see it, and for good reasons. I do believe they are slightly ridiculous. However, we do need to study the diameters of certain droplets, and I'll try to give you some other examples. So if you have a pen, feel free to note them down right now, so you can get these easy points on the actual exam about the diameters of water droplets. So of course, drizzle will be 0.5 millimeter, and then from 0.5 to 5.5 millimeters of radius, we have the water droplets. Then of course we have snow grain, which will be below 1 millimeter. We have snow pellet from 2 to 5 millimeters. We have ice pellet, so this is below 5 millimeters. Meter code will be Papa Lima. Then we have hail, small grail below 5 millimeters, and Golf Romeo GR in meters, which is big hail above 5 millimeters. And lastly, we have the sand grain, which is 0.08 of a millimeter in radius. And lastly, and this is a bonus from an HPL question, what is the diameter of nasal spray water droplets? And this will be anywhere from 7 to 12 micrometers. So hopefully this helps you answer these questions. And here I'll just mention that drizzle, in the case of this question, is different from rain because it's very small. It has a much lower terminal velocity, so it goes down at around 4 meters per second, where rain drops at around 9 meters per second, and drizzle does not create any splash. So this is also important for the questions. The limiting factor for the size of water droplets, for rain droplets, is 5.5, because if the water droplet is any bigger than that, it will just split into two. This is why 5.5 millimeters is the maximum for rain droplets. And lastly, we're going into question number 7. So how does air pollution affect the presence of supercooled water droplets in the air? And it actually does affect the presence of supercooled water droplets in the air. And this is for a very good reason, because air pollution is nothing else but very, very small particles of either sand, dust, or dirt or smoke in the air. And water likes surfaces. Water will change phases if it has a surface, as we discussed before. For example, supercooled water droplets, as we discussed before, exist in liquid state until they touch something physical in that moment. For example, an aircraft fuselage or the leading edge of the wing, they will freeze automatically. And the same is true in case of very small droplets, like in case of air pollution, dirt or sand. They will immediately freeze and fall down. So the air pollution will reduce the presence of supercooled water droplets, because these will very easily change into small crystals of ice and fall down to the ground if not enough convective activity is there to keep them up. And here also remember that for the same reason, if the humidity is high and you have a polluted air, then these particles can act as condensation nuclei, essentially creating small rain and drizzle that can fall down because the water will condense on top of these particles. So for the answer right here, a large number of small particles in the air reduces the number of supercooled water droplets in the air. And this will be everything for today. Thank you so much for tuning in. I hope this was helpful. If you have any questions, as always, feel free to comment or ask on our Instagram channel. And for now, I wish you a fantastic day and good luck with your exams. Thank you and bye-bye.